Good evening, everyone, and thank you for joining this evening for the last seminar in our four-part series on nuclear technology. If you missed the previous talks, the recordings are available on our website at energy.nd.edu. This evening, we are very pleased to have two speakers who will talk about nuclear science outside the realm of nuclear power plants. We will take time for a few questions after each presentation, with time for broader questions after both speakers at the end. Our first speaker is Captain Mark Prokopius of the United States Navy. Captain Prokopius is a Notre Dame ROTC alum from the class of 1990 and majored in electrical engineering. He has been back on campus as professor of naval science and senior commanding officer in Notre Dame's Navy ROTC since 2017. He has held many leadership roles and earned multiple service awards and commendations during his years of service. This evening, Captain Prokopius will share his extensive knowledge of the nuclear Navy. Thank you for your service and thank you for joining us tonight. I'll turn the slides over to you. And if you could unmute your mic.
I am unmuted. Yes, good evening. Hopefully everyone can see the slides. I'm Captain Mark Prokopius, as Ginger said. Thank you, Ginger, for that kind introduction. I have been in the Navy for 30 and a half years right now. Basically, I'm statutorily retired because you have to retire after 30 years, but the Navy decided to keep me on active duty for an extra year. So I've got 6 months left, and I will actually retire out of the service on the 1st of September of this year. So I am now actively searching for my next project that I will do after I retire from the Navy. I have been on 5 different submarines. I started off on USS Tecumseh, an old ballistic missile submarine, which is part of the 41 for Freedom that were built back in the 60s and 70s. And then continued on. I did new construction on USS Tucson, and I actually was the engineering officer to watch when we took that reactor critical for the very first time. Following that, I was engineer officer on the Hyman G. Rickover, and we'll talk about Rickover here in a second. I was XO on the USS Norfolk. I commanded USS New Mexico, a brand new Virginia-class submarine, and took her critical for the first time also. But I wasn't the operator. I was just in command at that time. Then my major command was a submarine tender out in Guam. Submarine tenders there's 2 of them in the Navy. And basically what we can do with tenders is we can go anywhere in the world and do nuclear repairs. And so that it gives you this autonomous floating repair ship that if somebody would break somewhere, remotely, I could go there and fix them. So I'll go through these slides really quickly. Here's the guy, Admiral Rickover. This is who started the Navy, the nuclear Navy. In 1946, he went to Oak Ridge, Tennessee, and you're basically looking to bring it back. They went back to DC and the Bureau of Ships, and he started the nuclear Navy, Naval Reactors. He served as an active duty officer for 63 years. I did not interview for the program with Admiral Rickover. There are some, very interesting stories about about the way he would interview officers. For example, he would make them stand in a closet for a period of time to see if they could stand being in a tight and closed space. And it was a lot of stories about that. I actually interviewed with Admiral McKee, which was the 2nd Naval Reactors. I did that my senior year at Notre Dame. So in the fall of 1989 was when I went up there. It was a great time, and he is credited. One of the things that we do in the nuclear Navy is one of the things that he is credited of saying is you get what you inspect, not what you expect. And so we have a highly intense inspection process that we go through on every year. So he was the father of USS Nautilus, and that's Nautilus. Nautilus was launched basically on 17, basically went underway for the first time in 1955, signaled they underway on nuclear power. And so we'll talk through some of these, why we do this, but before, so she was in commission until 1980, and she herself steamed nearly 500,000 miles before decommissioning. She's now a submarine museum up in Groton, Connecticut. You can actually tour the USS Nautilus, but only the forward compartment, because all of the reactor or the engine rooms and reactor compartments remain classified. So you cannot get an unclassified tour of any engine room or reactor compartment on any U.S. Navy ship or submarine, due to the fact that the systems that are actually classified confidential restricted data, just the systems themselves. So why do we have nuclear power? Why does the Navy use nuclear power? Unlimited cruising range. Rarely requires refueling. As a matter of fact, as the reactors that we now are including in our ships or aircraft carriers and submarines will likely not have to be refueled before we decommission the submarine and or the aircraft carrier. A reduced reliance on those outside air, long periods of time at high speeds, and logistic support. So on my submarine, I am limited only in the amount of time I can spend at sea by the amount of food I carry. And that is, I can carry up to roughly about 100 days of food. And so that's the only limiting factor. So when I go on deployment, I turn my my chill box into a freezer. I take nothing but frozen food, no fresh food at all. And then I basically load up throughout the entire boat. I'm walking on number 10 cans of food, and you basically eat your way through the cans as you're that are stored inside the passageways. That's really the only thing that limits me. When we load meat, we bring nothing that has bones. So everything's boneless and things along those lines as we eat our way through. Now, there are some disadvantages. You got this higher cost, higher maintenance cost. There's a lot of administration. You got the public regulations that you have to follow. There is some political unpopularity with the fact that that you are nuclear powered, but it's what we cannot conflate is you cannot conflate nuclear powered submarines with submarines that carry ballistic nuclear missiles, nuclear weapons. This is why we use nuclear power for our submarine force. There are significantly more personnel required for operation, and there's a lot of training that goes along with it, and I'll talk through that here in a minute. But for example, if on a conventional submarine, if I pull into port, I can just shut the submarine down and then walk away and not have to be on board. Our nuclear reactors in the Navy are monitored 24/7, 365. Okay, so I've got watch standards, even when that reactor is shut down, that they're maintaining the safety of that reactor. So we've seen pictures like this before. We use pressurized water reactors in the Navy. Okay, they have the primary system closed loop, pressurized to very high pressure. Steam generator is where the heat exchange happens between the primary and the secondary. And then that steam then goes into the engine room and turns my turbines, or as well, both for propulsion as well as for electrical generation. So very simple, simple closed systems. And then I just refeed the water back in the steam generator from the secondary side, heat it back up and recycle it. Same thing with the primary side. I just feed it around. Now, why pressurized water reactors? Okay, they're inherently safe, because we use water as our moderator. And while we use water as the moderator, it's very, very efficient to slow down those neutrons from the fast, high energy neutron that gets produced from a fission of a uranium atom, because I want them thermalized. I want them at that lower energy. The lower energy is more efficient for causing fission. So what I do is, if I'm taking a neutron and I'm bouncing it off a hydrogen atom, there's a bunch of hydrogen atoms inside of water. Okay, so H2O is what I use to slow it down. Now, as basically, if the amount of heat generated in the reactor is more than that's removed in the generator, the coolant's going to heat up. Well, that coolant heating up is going to have that coolant being less dense, fewer hydrogen atoms per volume to do those reactions, take longer to slow down, and more of those neutrons might leak outside of the reactor itself, therefore driving power down. So I'm inherently, because of this negative temperature coefficient of reactivity, we are inherently safe. Now, I know Professor Burns talked in the first lecture about, okay, that can be bad if you get too hot, okay, because of the Zerk water reaction. But if you think about it from keeping a core covered and making sure you don't get to that, we've got many systems and redundant systems that keep the core covered, with the final, basically the last ditch effort would be seawater. I've got a volume of a whole lot of seawater out there to use if I needed to. So from a Navy perspective, so here's some stats. I right now have 97 reactors in operation. That goes across the board, including prototypes and more training ships. And I'll talk a little bit about that. In the history of the Navy, we've operated 555 total. And right now I've got 70 nuclear powered submarines. That's broken down in the fast attacks, which are primarily, they are the ones that are anti-surface and anti-submarine, basically attack submarines. I also can launch cruise missiles from them. I have 14 SSBNs. That's 1/3 of our strategic deterrent triad. And we have 4 of the older SSBNs were converted into SSGNs. It's a guided missile submarine. And basically what we did is we removed all of the missiles off of them and loaded all of those missile tubes with Tomahawk land attack missiles. And so those carry a lot on the order of 140 Tomahawk missiles per SSGN. There's 2 on the East Coast, 2 on the West Coast, and they are constantly forward deployed. As a matter of fact, when I was in Diego Garcia on the tender, I did an upkeep for one of the SSGNs over there, USS Florida, that was on their deployment. We also do have our nuclear powered aircraft carriers, 11 of those, and we've had 7,300 equivalent reactor years of safe operation with 168 million miles steam. So we have not had any of the accidents in the nuclear Navy that we talked about earlier, like Professor Burns talked about. So how do we do this? Okay, we take it very, very seriously. If we did have an accident, okay, there would be radiation health concerns for the sailors and the public. Okay, there might be significant environmental concerns and this diminished image for the Navy and nuclear power. But most importantly, it's this loss of access to these ports. We have the ability to pull into 150 ports in 50 countries worldwide. And there's something to be said about being able to pull an SSGN or a carrier into Busan, South Korea, or into Subic Bay, Philippines, or into Vietnam. That's what our near peer competitor is operating in that area, and we're able to show that we can operate in that area as well and are welcome in those countries. Now, how do we do this? Okay, highly trained operators. So the pipeline, once both for enlisted and for officers, everyone basically graduates from college, and the first thing you're going to do, these are the officers. First thing you're going to do is you're going to go down to Charleston, South Carolina, and you're going to go to 6 months of nuclear power school. And basically that 6 months is just intense 6 months of training on all the theory, all the background, all the systems that go into our reactors. Okay. After that 6 months of training, you do 6 months of actually operating a prototype reactor. Right now we have 1 prototype up in New York, and we have 3 more training ships that are down in Charleston as well. Those more training ships are converted submarines that have been converted to do shore-based training. They're actually operating in the Cooper River, 3 nuclear reactors sitting right there. And one of them right now is a retired 688. 2 of them are the old ballistic missile submarines that like Tecumseh that I was on, and we're converting a second 688 submarine right now to take over. And eventually there's just going to be those 2 688 class submarines that have been refueled and redesigned. We follow procedures. we have a reactor plant manual that, that has procedures for every single possibility that could happen. We follow those procedures using Circle X method, i.e., once you go through the procedure, you circle the step that you're on. Once it is executed, you exit off and you go to the next one. Okay, we do that now electronically because all of our RPMs are actually online. Again, all of our RPMs are confidential restricted data, so I can't go specifically into that. These yearly testing of operators. This is one of the jobs I had in the Navy. I basically, what we do is on an annual basis, you have an operational reactor safeguards examination where an external organization comes down and examines you. Okay, this will go to some of the concerns that during the second lecture that we talked about, that concerns of that the Nuclear Regulatory Agency was that self-looking ice cream cone. Where this is an independent. These people, this team that I was on, we don't work for the subforce, we don't work for the surface forces, we work for Fleet Forces Command. So it's that independent look that does level of knowledge. We basically go through some drills and casualty training. You do oral interviews, and then you do a material inspection of that plant, as well as and a whole walkthrough, as well as a 100% administrative review. That happens on an annual basis. And again, like I said, we are inherently designed for safety. Those reactors are designed to withstand battle damage or battle shock, and still continue to operate. If any of you remember when USS San Francisco was transiting in the South China Sea, basically she was transiting from point A to point B, ran into a submerged seamount at full speed, and was able to, and that reactor remained operational. And so that's the type of resiliency that our reactors have maintained. So let me shift gears here a little bit. So if you're excited about the Navy nuclear propulsion program, there's an opportunity for you. So if you're even if you're a graduate student and you want to join, you can. Okay, you can go operational or support, and it's called the Nuclear Propulsion Officer Candidate Program. Submarine officer, you surface warfare officer, that'd be the surface warfare path. You'd be on a carrier. Submarine, you're going to just be on a submarine, or you can support to be a nuclear power school. That instruction I talked about down in Charleston. An instructor at those nuclear power training unit, those MURR training ships that are down in Charleston, or you don't do anything and you go up to Naval Reactors and work for the Admiral up there as an engineer. Let me back up really quick, back up to these highly trained operators. So one of the other things too is every single officer that gets put into the program interviews with Naval Reactors. So you do a couple technical interviews with those Naval Reactors engineers, and then every single one of them goes up in front of the 4-star. As a matter of fact, one of my midshipmen today, 2 of them passed their nuke interviews, or my last 2, and Midshipman Leaker, it was Admiral Caldwell's 4,000th interview that he had done with midshipmen, and it was kind of cool. So let's go back to DuPont. So what are the benefits if you want to do this? Hey, you can join up to 30 months before you complete your degree and get paid as you're on active duty, but you don't have to do anything. You don't have to go to drills. You don't have to go in uniforms. You don't have to, you can grow a beard. You can, no grooming requirements, full medical and dental. It counts towards your time in service. So your retirement. So that 30 months can go. You got that guaranteed job. If you want to operate a nuclear reactor at sea and fight the ship, it's great. You get this succession bonus if you're going into the operational side, an additional bonus upon completion of training. But you're going to have to give the country back some time. So 5 years upon commissioning. And then there are in the Navy, there's graduate school opportunities. I actually got my graduate degree from Old Dominion University when I was on shore duty via a graduate education voucher program. So I have a master's in engineering management from Old Dominion. It's been fantastic. So you can earn about $150,000 if you join at that 30-month point. But there are some requirements. Sorry. You do have to be enrolled as a full-time student at an accredited institution. Hey, Notre Dame is an accredited institution, so we should be just fine there. You do have to be a U.S. citizen. You have to complete 2 semesters of calc and physics. And again, if you are in a post-grad degree and you're in a master's degree, you can still join, but you just have to be within 12 months of your graduation. So that is my pitch right now. This is a 688 class submarine that is coming out during an emergency surfacing procedure, and you come out of the water about 20 knots. It's a pretty interesting ride.
All right, thank you very much, Captain Prokopius. Are there any questions? You can use the raise hand function or type them in the chat. So one question is, what are civilian jobs or research jobs involved on these subs, or are there any?
There are not. Let me try to stop share. Hang on a second. There we go. Oh, thanks. There are not. There are contractors that come on board that might fix things, but there are really the Navy is fully manned by active duty, enlisted, and officer personnel. Great question.
All right. Are there any other questions? If not, we'll hold your questions till after our second speaker.
Great question about the thresher. Okay, so
Okay.
there's a question in chat about the thresher that happened. So the Navy has lost 2 nuclear submarines to catastrophic accidents. Thresher was lost on sea trials. They think due to a catastrophic failure of a seawater system that then basically resulted in the Navy adopting what's called the sub-safe program, and basically went down with all hands lost and went down and imploded, went down below crush depth. A similar thing happened to the Scorpion. Not quite sure. There's a lot of conspiracy theories about what happened to Scorpion, but she too is at the bottom of the ocean. Now, what the Navy has done is those reactors remain completely intact and remain completely intact to this day. There's been no breach in the primary shield. There's been no breach in the primary system. The Navy has done several surveys of both of these sites, some as recently as 1998, that have shown no increase in any fission product in those areas in the soil samples inside of on the seabed. So those reactors are now basically entombed at the bottom of the ocean and are going to remain there, and to this day have not been breached. Great question. So scaling nuclear technology, widespread civilian power. It's really we do use the same as the nuclear power industry. We're just smaller. We are a submarine reactor is about 1/30 of the power of a normal civilian plant, and the carrier reactors are about the 12th. We're just smaller. So we use pressurized water reactors just like the civilian industry uses pressurized water reactors. It's the exact same technology, the 2 closed loop systems. But there's really no different technology from that we use. Now, from a training perspective, there might be some, the way that we approach things, the way we inspect, the way we we hold everybody accountable. That might be something that can be applied into the civilian world. But as far as the technology is the same. Great question.
All right, thank you, Captain Prokopius, and we'll save any remaining questions to the end of the second talk. So I will now introduce our second speaker, Professor David Robertson, chemistry professor at the University of Missouri and director of the MU Research Reactor. His research focuses on radiochemistry, nuclear chemistry, and analytical chemistry with broad applications for neurological disorders, environmental science, and archaeology. Dr. Robertson earned his BS from the University of Missouri and his PhD from the University of Maryland. We are pleased to have you, Dr. Robertson, with us this evening. I'll let you take the slides.
Thank you, Ginger, for the kind introduction, and thank you for inviting me to share about the Research Reactor. So let me bring this up. And while I'm doing so, I'll put in a plug for Dr. Prokopius, Captain Prokopius's talk. Most of my operators of our Research Reactor come to us from the nuclear Navy. We love them. So if you go in and you decide after a while you want to do something a little bit different, there's a nice career path. So, okay. And now move this a bit out of the way. And so what I wanted to share with you this evening are a couple of applications of the Research Reactor here at the University of Missouri. The title of my talk is From Out of the Blue at MURR, and the blue makes reference to what you can't see in a power reactor because the pressure vessel is all buttoned up. But what you see here is the Cherenkov radiation as our reactor is running at 10 megawatts. You're looking down through about 30 feet of water, and there in the center, the engineers would call it a pressure vessel. I call it an aluminum pipe because we do not run anywhere near the pressures that you heard about in the previous talk. So a little background. MURR is a 10 megawatt thermal research reactor. We operate 24 hours a day, 6.5 days a week, 52 weeks a year. Quite frankly, we could not do that without the excellent staff, many who came to us from the nuclear Navy. MURR is the largest reactor at any university in the United States. The second largest reactor is at MIT, which runs at 6 megawatts. We are both a research and a production facility, and as such, as a research center on a campus, we have a lot of staff. We currently have 185 full-time employees. In 2020, and I've also shown you here the numbers for 2019 if you're interested in the impact of the pandemic on what we do. In 2020, we produced 29 different radioactive isotopes, and we made 1,700 shipments of those isotopes to 8 different countries. Each and every week, MURR supplies the active radioactive ingredient in a number of drugs. Quadramet, Therospheres, Lutathera, Iodine-131, and radiogenics. I'll tell you about the first 4 on my next slides. Radiogenics is, we supply Moly-99 for use in a generator of technetium-99m. When used in this way, technetium-99m is used as an imaging agent in nuclear medicine. We don't supply enough Moly-99 to meet this demand I'm about to tell you about, but technetium-99m is used in over 30,000 times a day in the United States. It is the most used nuclear medicine isotope. So here's a picture, a schematic, a top-down view of the research reactor. Our core consists of 8 fuel elements in an annulus. In the center of the core is a region that we call our flux trap, where we can place materials to interact with the neutrons from the fissioning uranium in the reactor. And then outside of the pressure vessel are another set of irradiation positions that you see here, where we can also place samples. The highest neutron flux is in the center of the reactor. So this is where we do most of our medical isotope production. And a lot of our material science and research samples are placed out here. So because of the research reactor, a number of radioactive drugs or radiopharmaceuticals have been developed at the University of Missouri. One was Ceratec, which uses technetium-99m. In this case, The technetium-99m is in a molecule that can move through the brain-blood barrier and allow the physician to image blood flow in the brain. Again, this is feasible because of the low energy gamma ray that technetium-99m emits in its decay. Second example is quadramet. It uses the radioactive isotope samarium-153, which emits beta particles in its decay. And the samarium-153 is encapsulated or bonded with a ligand that has a lot of phosphorus in it. And so when quadramet is injected into the bloodstream, it naturally goes in your body to where there's a high phosphorus turnover, which is happening if you have metastatic bone cancer. And so quadramet delivers the radioactive isotope to the bone cancer because of its chemical nature. And then the beta particles from the decay of the samarium-153 kill part of the cancer, which eases the pain associated with the bone cancer. Typically, a patient who receives quadramet will come into the hospital in a wheelchair. The pain from the bone cancer is quite severe. After 1 to 2 treatments of quadramet, that patient will leave the hospital, walk out of the hospital, and they're pain-free from the bone cancer for anywhere from 6 to 18 months. The third example is Therosphere, which is a glass microsphere in which we put yttrium. The microspheres are about 20 microns in diameter, about the diameter of a human hair. And their size is designed so that if we inject them into a capillary that feeds the cancer in your liver, because the cancer is growing so rapidly, the capillaries are naturally undersized. And so the microspheres stick in the tumor because of that. And then the yttrium-90 gives off a high energy beta particle that kills the cancer cells. In the case of Therosphere, again, it's used to treat patients with inoperable liver cancer. So these are quite sick people. But on average, 70% of the people who get a Therosphere treatment go into full remission. Again, the Research Reactor each and every week makes the samarium-153 and irradiates the Therospheres. We also, on a weekly basis, now make radioactive iodine-131. Iodine-131 is the second most used isotope in nuclear medicine. If you swallow iodine, it naturally accumulates in your thyroid. And so if we give you radioactive iodine and you have thyroid cancer, the radioactive iodine goes to the thyroid near the cancer, emits a beta particle, killing the cancer. Now, this was the first radioactive drug approved by the FDA back in 1951. Since the 1980s, it was no longer made in the United States. It mostly came from a reactor in Canada that has since stopped making iodine-131 and moly-99, and it comes from several foreign reactors. Knowing that the reactor in Canada was going to shut down, we put together a business plan for our university, and they funded us so that we could set up the production line that you see here with the hot cells and the manipulators to make iodine-131. We do that by irradiating tellurium oxide targets in the reactor. The tellurium captures a neutron, becomes radioactive tellurium, and decays into radioactive iodine. And then we separate by distillation milligram quantities of radioactive iodine from hundreds of grams of the tellurium oxide. This is while it's been used for a long time, it's a very important isotope. Thyroid cancer is the most rapidly increasing cancer in the United States. We don't know why. It's the most common cancer in women aged 20 to 34. But the good news is, for people who get iodine-131 for treating thyroid cancer, the 5-year survival rate for those patients is better than 98%. And the last example that, just to put it in perspective, what kind of team does it take to make radioactive iodine on a weekly basis? What you see here are engineers, health physicists, health physics technicians, quality engineers, quality control technicians, people who take care of shipping, and people who take care of running the reactor. So it takes a lot of folks to make this and send it out every week. And what you see in the front of the group is the 350-pound cask that the radioactive iodine goes in to go on a truck to be shipped out to the radiopharmacies around the country. My last example for you of a radiopharmaceutical is targeted radiotherapy. In this case, we call it peptide-targeted radiotherapy. What we're doing here is using a small peptide, octreotate, as the molecule that targets a somatostatin receptor on tumor cells to drag the radioactive isotope along to the tumor cell. We attach a DOTA ligand that you can perhaps just make out here. And then the DOTA binds the radioactive lutetium-177 that we make very tightly, and so delivers this radioactive isotope to the receptor on the tumor cells. Now, MURR produces each and every week the lutetium-177 for the United States, and there are several weeks during the year where we produce all of the lutetium-177 used in the world for this drug, which is called Lutathera. Lutathera was developed by a small company called Advanced Accelerator Applications, and when the drug was approved by FDA in January of 2018, Novartis purchased Lutathera to take over the supply and distribution of this drug. This drug treats neuroendocrine tumors of the midgut that express these somatostatin receptors. An example would be pancreatic cancer that has gone undetected and metastasized. And so this is the kind of image that you would see from such a patient with the cancer spread throughout their abdominal cavity. The good news, and this really motivates us here at the Research Reactor, before this drug was developed, if you had pancreatic cancer that metastasized, your average overall survival using standard cancer care was something on the order of 6 to 8 months. We are seeing patients with overall survival benefits of greater than 5 years who are receiving Lutathera. So it's really an effective drug, and it's really changed the nuclear medicine community and industry, as many more companies are now working very hard to develop additional targeted radiotherapy agents for example, prostate cancer or breast cancer, among others. We make lutetium-177 in 2 ways. Lutathera currently uses lutetium produced by starting with a target of enriched lutetium-176, which captures a neutron and becomes lutetium-177. This method works great, but using the direct method, a small fraction of the radioactive lutetium, about 0.3% in the lutetium sample, is the longer-lived metastable lutetium-177M with a 161-day half-life. It's perfectly fine to use in the patient, but it makes the use and distribution and cleanup from using the drug difficult and expensive for the hospitals. So the nuclear medicine community would like to have lutetium-177 that doesn't contain any of this metastable, long-lived lutetium. So the way that we do that is we start with an enriched ytterbium-176 target, as you see here, and that captures a neutron, becoming ytterbium-177. It has a half-life of approximately 2 hours, and so while we're irradiating it, this is decaying, becoming lutetium-177. And because of the nuclear properties, you only make this the 6.65 day lutetium. You don't make any of the long-lived metastable. And so over the last 2 years, we've developed a way to do this. And I'm happy to tell you that we've just, and I can tell you about it because it's a public announcement now. We've recently signed a contract with Novartis to be the US supplier for them for making lutetium by the indirect method. Just to put it in perspective for you, what do these targets look like in the reactor? Here are 2 quartz vials. That's how we place something in the reactor to expose it to neutrons, to make it radioactive. And on the vial on the left, you see a little tiny dot. And that's about 1 milligram of enriched lutetium-176 nitrate. So irradiating that 1 milligram sample in the reactor would make about 30 curies of lutetium-177, which is enough to treat several hundred cancer patients. Again, the downside is the coexistence of that longer-lived impurity, and only a fraction of the lutetium atoms in the sample are radioactive. So when you put them in this drug, only 1 out of every 4 of these drug molecules deliver a punch or radioactivity to the receptor, because the other 3 lutetium atoms in that sample are not radioactive. In the indirect method, because of the nuclear properties, we have to start with a much larger mass of ytterbium-176 oxide. You see here 350 milligrams in a quartz vial. But when we make the lutetium this way, first, we don't have the long-lived impurity, and second, nearly every lutetium atom in our sample, because we chemically separate the lutetium from the ytterbium, nearly every lutetium atom in that sample is radioactive, and so every lutetium atom in the drug is delivering a punch to the cancer cells. So I would end my discussion on our use in nuclear medicine and just point out that the Research Reactor here at the University of Missouri is the only supplier in the United States of iodine-131, samarium-153, Therospheres, lutetium-177, and we're the only domestic producer of molybdenum-99 for technetium-99M generators. And we think this is our mission. We take it very seriously. And because of those outstanding operators that came to us from the nuclear Navy, I never have to answer this question. But if we don't run this week, cancer patients don't get treated next week. And that's why we work so hard to run 52 weeks a year. I'll end with a different application of the Research Reactor. In this case, we'll use the reactor as an analytical tool, not as a way to make a radioactive isotope. In this case, what we do is we place a sample in the reactor, and a target, an isotope of an element that we're interested in that sample captures a neutron. It becomes radioactive with a distinct half-life, and it's going to give off, for us in this technique, it gives off gamma rays. The energy of the gamma ray tells us what target nucleus captured the neutron, and the number of gamma rays per second emitted from the sample after the irradiation tells us how much of that target nucleus is in the sample. There are real advantages to neutron activation analysis. One, because the sample is transparent to neutrons. There are very few materials that neutrons don't just travel through. and the sample is transparent to the gamma rays, it doesn't matter what's in the sample. We're going to get the right measurement as we move from, for example, a piece of tissue to a piece of bone to a rock or a piece of coal. It's very easy to standardize because it's matrix independent. It's non-destructive in the fact that I don't have to take your sample and chemically dissolve it to do an analysis. All I have to do is place your sample in the reactor for some period of time, take it out, and measure the gamma rays that are being emitted from the sample. And because I don't have to dissolve or prepare the sample, then the chance that I would contaminate the sample either with a reagent or something in the laboratory is really minimized. So if it's so great, right, why haven't you heard of it before? Why doesn't everybody use neutron activation analysis? Of course, there's one disadvantage of neutron activation analysis. You have to have a reactor. Fortunately, I have one, so it's not a disadvantage for me. And I'll give you an example of the use of neutron activation analysis. That's in measuring a trace element fingerprint in a volcanic glassy rock called obsidian. We're interested in obsidian because ancient peoples highly prized it. The ancient peoples learned how to pick up a piece of this rock from a volcanic site and hit it just right to make them either a blade or an arrowhead that gave you a very sharp edge. In fact, at the time, your options for a sharp edge among ancient peoples were obsidian or flint or bone or a stick. And of all of those, obsidian was by far the sharpest. So it was a very highly prized material. In understanding ancient peoples and their cultures, obsidian is nice because you can only get it from a volcano and there are a limited number of sources. Because it's a black glass material, we know that the ancient peoples didn't change the obsidian from where they got it to where they used it. And nature is kind to us in that most obsidian flows are very compositionally homogeneous. Now, you might have different flows on the same volcano, but all of the obsidian from the same flow gives you essentially the same fingerprint. And finally, as an archaeological tool, obsidian is kind of like my disposable razor. While it gives a really great sharp edge, it doesn't stay sharp for a long time. You needed a high rate of replacement. So when you go to an archaeological site, you will find lots and lots of samples of disposed obsidian. So it's a great way to understand the trade behavior of ancient peoples. On the left is a picture of the gamma ray spectrum that you would get from a piece of obsidian, irradiated in the reactor for 5 seconds, let it decay for 25 minutes to let some very short-lived radioactive signatures decay away, and then count it for 12 minutes. And you can see here very nice, strong signals for elements that we're interested in measuring to get the chemical fingerprint. So here is how we use the data. This is a plot of the obsidian sources in Peru and Bolivia, analyzed by neutron activation analysis. And even in just this simple two-dimensional, two-variable plot, it's quite easy to separate all the sources, pardon me, by simply plotting the concentration of lanthanum versus the concentration of cesium. Now, in our NAA work, we typically measure about 30 elements in the obsidian samples and do a multivariate analysis where you just separate out that 30 variable space, just as you see here. And so here's an example of what you can learn. This is a picture of an obsidian blade that was recovered from a dig in Spiro Mound, Oklahoma in 1935. It went to the Smithsonian and people forgot about it for a long time. In about 2000, a researcher by the name of Barker remembered this blade was there and asked to get a little piece of it, sent it to us here at the reactor. We did the neutron activation analysis, and compared it to the database that we have here at the reactor. And it was quite obvious that this blade came from this volcano in central Mexico. Believe it or not, this was the first physical evidence that the Native Americans of the Central America, Central United States, were in contact, were trade in some way with the high culture of the day in central Mexico. So that's the kind of thing that you can learn from this kind of work. And with that, I'll show you an overview picture of the reactor. The reactor is housed here inside of our containment building. And this is the rest of the research reactor facility. And I'm happy to take any questions.
Thank you very much, Dr. Robinson. Are there any questions? So there's a question about, could you speak about carbon-14 in the brain of the Alzheimer's patients?
Oh, thank you. I'll try to make that really quick. When you set off a nuclear weapon above ground, because of the neutron pulse from that nuclear weapon, you end up making lots of carbon-14. That carbon-14 turns into CO2, and it gets incorporated into plants, and then animals eat the plants, and people eat the plants and the animals. So ultimately, that carbon-14 ends up in people. And we, when I was at the University of Kentucky, we used a technique called accelerator mass spectrometry, which allows you to measure very tiny amounts of carbon-14 on brain tissue samples from people who lived back in the time that we had fairly large signatures of bomb pulse carbon-14 still around. And we use that signature to determine the age of the senile plaques and the neurofibrillary tangles that had formed in their brain as they developed Alzheimer's disease. I hope that partly answers your question. Otherwise, I have to get real technical.
All right. Can you speak a little bit about the capacity of your reactor? I mean, I know you said you're making the full supply for certain isotopes. Are you at full capacity with that, or is there room that you could take on more if a new isotope was discovered to be very helpful?
Great question. Thank you. So we are not at capacity in the most important part of the reactor for making medical isotopes. We could take on a new isotope production. In fact, we're doing that. Unfortunately, I can't tell you about it. It's under non-disclosure agreements with those companies. But we are getting close to being at capacity. And if, for example, we have a successful prostate agent that uses lutetium-177. It's in clinical trials right now by Novartis. It's called PSMA 617 as a way to deliver the lutetium to the prostate, the metastatic cancer from the prostate cancer. If that's a success, and if the solid tumor target that's being developed using lutetium for breast cancer is a success, I can tell you that I can't make enough lutetium-177 to supply the demand that will be there from the nation. So I'll have to make choices about what we do in our reactor. But even if I dedicated all of the flux trap of our reactor to making lutetium-177, we're going to need additional sources.
All right, thank you. Are there any other questions from the audience?
I see how much of my operating costs are covered.
Sure.
Okay, so we generate through producing isotopes and irradiating materials to change their properties and doing some analytical chemistry work with things like neutron activation analysis. We generate 90% of our operating budget for a center that has 185 full-time employees.
All right, I have another question. Is there any public concern about having the reactor on campus?
Oh, I love that question. You know, the public is a fickle beast. So 20 years ago, when I came to the University of Missouri from the University of Kentucky, we had to report an incident to the NRC. It had nothing to do with the operation of the reactor. It had to do with mishandling radioactive material and putting it where someone could have been exposed. No one was exposed, but they could have been exposed. So we had to self-report that to the NRC. And of course, if you want to sell newspapers, right, you look for something controversial. And so that immediately made it into the press. So 20 years ago, I would say to you that the administration of our university thought MURR was a four-letter word because they were dealing with negative press from the public and the NRC. Today, because of our communicating that what we do for saving people's lives in making medical isotopes, we are described as the crown jewel of the university. And I can tell you that when the business community and the general public tour the reactor, they love us. I'm not getting any negative press or issues that I'm having to address as the director.
Fantastic. All right, we'll open the floor one last time to both our speakers if there are any other questions. All right, well, thank you very much for joining us tonight, and thank you to everyone who has come the whole way with us and attended all four of our seminars, and I hope you all have a good evening. Good night.